All right, daily 2 number 41. Let's share the screen here. And it's this one. So 54.2 meters is equal to how many centimeters? And we're going to move the decimal point from meters to centimeters is 2 places, and it's going to be 2 places to the right. And so the correct response is 5,420. Okay. And as I look at the responses for this, most people came up with that. Not all, but most. It looks to be about 80% or so, which is still not quite where I want to be. The most common mistake was to move the decimal point 3 places instead of 2. So there are 100 centimeters in a meter, so that's why we only move it 2 places. Okay. And then the second one is, which of the following are examples of waves? And the correct response is, these are all examples of waves. Light is a wave, a tsunami, or what used to be called a tidal wave, but more properly, at least in my opinion, called a tsunami in the ocean, and then sound. These are all examples of waves. Okay. All right. And most respondents came up with that as well. So that's good. Now you may be wondering, I'm going to stop sharing now. You may be wondering why I asked that question. Well, that's because second semester is going to be based on waves. Okay, now going back to first semester. Oh, by the way, I'm not going to formally go over the semester 1 final exam. If you want to have me go over yours with you individually, I'm perfectly happy to do that. Just stop by during office hours, and I will be completely willing to do that with you. I will show you your exam, and we'll go through it together. Okay, so let's do that individually during office hours. Okay. Otherwise, we're going to move on. Now, I actually got through only about half the material, a little bit more than half the material I normally do in semester 1. And I was kind of debating over break whether I should finish up semester 1, which is all about motion, kinematics, motion, and all the things that affect motion, namely forces, but I didn't get to energy and momentum and things like that. And I was kind of debating with myself whether I should continue with that or move into semester 2 material. And after thinking about it for a while, I decided to go with semester 2 material. Okay, and semester 2 material it's a different area of physics. It's all about waves. Okay, and all the phenomena of waves and applications and things like that. And it's different than first semester. And I wanted to give you a taste of that type of physics as well. So I decided I'm going to just go ahead and do semester 2. Now, semester 2 is much less mathematical, which is probably good news for some of you and maybe bad news for others. It's more theoretical, much less equation based. There are equations, but they're not as involved, and there aren't as many. Okay, it's not as algebra heavy. Okay, it's more theoretical, more experiential in some ways. We've experienced a lot of things that we're going to be talking about, and the topics are going to be waves in general, general phenomena of waves, and we're going to talk about water waves a lot because we're familiar with that, and then we're going to go into sound waves, and then into light. Okay. And I would also like to bring electricity and magnetism in, given enough time, or at least parts of it. Okay, depending on time considerations. And if I have time at the end of the semester, and I certainly hope to have you you guys in my classroom before then, because I want to do some engineering activities. I want to build stuff towards the end of the year, some hands-on things that I normally do, and if I do have time, then I'm going to go back and talk about energy. I would like to get energy in before the end of the year. All right, so that's the agenda for second semester. All right, so we're just going to go ahead and dive into waves. It's going to be new. All right, we're going to I'm going to start out basic, and then we're going to apply basic stuff to specific situations. All right. So, yeah. So we're going to leave motion behind for now. All right. Okay. So having said all that, you're going to need something to write with, something to write on. We're going to start a new unit today, and that unit is about waves. Okay. And I have a PowerPoint presentation that I'm going to go through. And all this stuff is posted on Schoology in this week's folder, the PowerPoint presentation I'm going to go through, the class notes that I work from. So you don't necessarily need to write all this stuff down because you can access it from Schoology. Okay. Okay, I'm going to go ahead and share the screen once again. And we're going to talk about waves. Okay. Today is going to be very vocabulary heavy. I have to introduce a lot of vocabulary today. All right, we have to get some academic vocabulary down, and so that we can talk about other stuff successfully. All right, so it's kind of a vocab heavy day. All right, I want to leave the last 15 minutes of class or so. We're done at 10:05. I want to leave the last 15 minutes for you to work on a Waves Worksheet 1, which is some homework that I'm going to have due later on. Okay? All right. So let's get into it then. Waves. So now there are two ways to transfer energy in nature. Okay? The first one involves collisions. Okay? One thing banging into something else. And that's a way to transfer energy from one place to another. And as a kind of goofy example of this, I have bowling. So I got this little YouTube video that I'm going to show. Right. Turn the volume down. So you got this guy bowling. It's kind of sketchy. And so he transferred energy from one place to another. And he did this by chucking a ball down the lane. Okay. And this is transferring energy from here, where he's standing now, to some 40 some odd feet away. I can't remember the length of a bowling alley, but 40 feet long away or something, to the pins down there. And this is a transfer of energy, but this is also involves a transfer of matter. Okay. To get the energy from one place to the other, he had to transfer a ball from one place to another, namely here to there. So this transfer of energy involves a transfer of matter. Okay. And notice the guy in the other lane did the same thing. Transferred energy by transferring matter from one place to another. And we'll just watch this guy do this one more time. Transferring energy by transferring matter. What? What just happened? He's saying, I'm so good, I can get a strike on your lane. Check that out. That's a 1 in a million, eh? Yeah. One more time, just for fun. Transferring energy involving a transfer of matter. Okay? Okay. So that was kind of goofy. But now that's bowling. But now another example of transferring energy from one place to another is, oh yeah, sorry. I don't have my binder in front of me because it's in my room, so I'm forgetting this stuff. So my progression of slides here. Anyway, it involves a transfer of matter from one place to another. Another way of that energy is transferred in nature is the sun. The sun is transferring energy to us all the time. Okay. Now, what if the sun transferred energy to us via a transfer of matter? What would happen to the sun if it transferred energy to us with a transfer of matter? What would happen to the sun? Anybody want to guess? If the sun transferred energy to us via collisions, what would happen to the sun? Anybody want to guess? It wouldn't explode so much as it would get smaller. Yeah, it would basically evaporate. Yeah. So, and it wouldn't take all that long either. And so there's no way we could exist if the sun transferred its energy to us by transferring a matter, by transferring matter. Instead, it transfers it via a wave. A wave, okay, a wave involves a transfer of energy without a transfer of matter. Okay, and that's key. If there were no such thing, then we wouldn't exist. Okay, because the sun would evaporate, all the stars would evaporate very quickly. Okay, so we need to have a mechanism to transfer energy without a transfer of matter, and that is a wave. Okay, it's a transfer of energy without a transfer of matter. Okay, now there are two basic types of waves. All waves can be categorized as one of these two types. Okay, one of them is called a transverse wave. All right, and a transverse wave is a wave in which the particles of the medium vibrate perpendicular to the direction of wave travel. Okay, now again, these definitions you don't necessarily need to write these down. You can access these through Schoology. Okay, through this presentation, which is on file in the folder. Okay. All right, an example of a transverse wave is a wave in water. Okay, I'm going to use the example quite a bit today of bobbers in water. And let's say that you are out fishing with a friend. Okay, you're out in a boat in the middle of a lake, and it's 7 o'clock on a summer evening, beautiful evening, no wind at all. So the surface of the water is flat, like it's glass-like surface. Okay, and you have a couple of bobbers out in the water there, and the fish aren't biting, so the bobbers are just sitting there. And and you're enjoying your conversation and stuff. And then a speedboat goes by about 40 meters away, and you're a little bit bored because the fish aren't biting. So you watch the waves as they approach the location of your bobber, and they pass through the location of your bobber. Okay, the waves travel horizontally on the surface of the water, and when they get to the bobbers, the bobbers move up and down. The bobbers bob vertically. The motion of the bobber is vertically, while the wave is horizontal. Okay. Now a bobber is just a visible particle, but each water molecule does the same thing. The water molecules vibrate vertically, while the wave travels horizontally. Okay. So the particles of the medium, that is the water and the bobber, vibrate perpendicular to, vertically, the direction of wave travel, which in the case of a water wave would be horizontal. Okay, so that's an example of a transverse wave. Its counterpart is called a longitudinal wave. And a longitudinal wave is a wave in which the particles of the medium vibrate parallel to the direction of wave travel. Okay, every word is the same in here, except for parallel versus perpendicular. And I'll give you a few moments to write that down. Okay. All right. Okay, I just wanted to, a couple of latecomers, I wanted to get in attendance. Yeah, all right. And an example of this would be waves in a slinky. Okay, and so here's a slinky representation of one. And if you agitate one end, this wave is going to travel down the slinky like this. And each coil is going to vibrate back and forth in the same direction, not up and down, but back and forth as the wave travels down the slinky. This would be an example of a longitudinal wave. Each coil of the slinky would vibrate to the right and then to the left, okay, to the right and then to the left as the waves travel from left to right. That's an example of a longitudinal wave. Okay. All right. Okay. Now, so each wave that we talk about will either be transverse or longitudinal. Okay. All right. Now there's some vocabulary that's particular to each of these and common to each of these, and I want to go through those as well. So I'm going to advance this. Okay. Remember, I'm recording this, so if I'm going too quickly, first of all, let me know, so I'll go back. But longitudinal waves are rather difficult to draw, so most of the time we're going to use a transverse wave as a diagram. Okay, so sketch yourself a little transverse wave here. All right. Now, I have this dashed line here, this dashed line. This represents the surface of the water, and again, I'm going to use water as an example. This represents the surface of the water before the speedboat went by. It's a glass-like surface. All the particles of the water are at rest. There's no wave traveling through it. This is called the equilibrium position, or sometimes called the rest position. Okay, it's the particles of the medium before the wave traveled through. All right. Now, so the speedboat went by, and the waves are passing through the locations of the bobbers, and this is a snapshot of the wave from a horizontal view. Okay, the top of the wave is called a crest. The top of the wave is called a crest. The bottom of the wave is called a trough. Okay. All right. Now, crest and trough are particular for transverse waves. Now I'm going to stop sharing for a moment. Okay, and I'm going to go with my camera here so you can see. All right. And so I'm going to draw a transverse wave. There's going to be my rest position. There's going to be a transverse wave. Okay, the top is called a crest, and the bottom is called a trough. Okay. Now, longitudinal waves are more difficult to draw. For example, the slinky, I'm going to draw a slinky. Okay, and I'm going to first draw it at rest. So I'm going to have a kind of a slinky like this. And that's just going to be, sitting on the tabletop before a wave goes through. Then I'm going to jostle one end, okay? And the coils are going to get closer together. And then as the wave travels down the slinky, they're going to compress, and then they're going to get closer together, and then they're going to get farther apart. So if I draw this, I'm going to draw them close together, and then I'm going to draw them farther apart. And then I'm putting closer together, and then I'm going to draw them farther apart. Okay? Where they're closer together, this is called a compression. Okay? Where they're spread out, this is called a rarefaction. Rarefaction. Okay? Next time when I'm in my room, I will actually show you this with a slinky that I have there. Okay? All right. Longitudinal waves are also sometimes called compressional waves because they have compressions and rarefactions. Okay. Now these terms are particular. Crests and troughs are particular for transverse waves. Compressions and rarefactions are particular for longitudinal waves. Everything else that I'm going to talk about is common to both. Okay. Okay. We'll share the screen again. Let me get back into my PowerPoint. All right. Now, we can talk about the distance between one crest to another crest, and that is the length of one complete wave. The length of one complete wave, and we call that wavelength. Okay? Wavelength is the distance of one complete wave vibration. One complete wave vibration. And it is the crest to crest distance, okay? Or trough to trough distance, okay? It's the length of one complete wave. All right. Now we represent this. We're going to end up having an equation with wavelength in it, and we're not going to use W for wavelength because W is used for other things in physics. Instead, we're going to use a letter from the Greek alphabet, which is we're going to use the Greek letter lambda, which is shaped kind of like an upside down Y. All right. So lambda is used to represent wavelength. Okay. All right. Now I'm going to stop sharing once again because I want to get to my thing here. So wavelength would be the crest to crest distance. You guys see that? Wavelength. All right. Or trough to trough distance. Or the distance from here to there. Okay. It's the distance for one complete wave, one crest and one trough. For a longitudinal wave, it would be the distance from compression to compression. That would be a wavelength, from one compression to the next compression, okay? Or length from one compression and one rarefaction, one complete wave vibration, all right? That's the wavelength. Or rarefaction to rarefaction, all right? Okay, I'm going to share once again. All right. Okay, another term is called amplitude. Okay, amplitude is the distance from the equilibrium position to the crest of the wave. All right. Now you have to be careful with this. So on my diagram, I'm going to label it like this. It is the distance from the equilibrium position to the crest. Okay, or the distance from the equilibrium position to a trough. It is not trough to crest distance. Okay, it is not trough to crest. It is from the equilibrium position to the crest. Okay, be careful about that. Now, I'm not going to talk about the amplitude of a longitudinal wave because it never comes up. We never have to draw that. We never have to measure that. So I'm not even going to bother putting that on my longitudinal wave diagram. Okay, I suppose we could talk about it, but we just never do. All right. So that's the amplitude. Okay, it's the maximum displacement from the equilibrium position. Okay. Okay. All right. Next. Now, let's say that this vertical dashed line represents the bobber, okay? And and the horizontal dashed line is the equilibrium position. So let's say you're out there, you're out fishing with a friend in the lake, and the fish aren't biting. And a speedboat goes by, and a wave passes through the location of your bobber. All right, and you're bored, so you want something to do. So you say, "Hey, Jamie, get out your watch. I want you to give me a 10-second count, and give me a 10-second thing because I'm going to count how many times the bobber goes up and down in 10 seconds." All right, you're bored, so this is what you want to do. So Jamie says, "Okay, start," and the bobber goes up and down. You go up, down, 1, 2, 3, 4, 5, ... Jamie says stop, and you counted 20. So the bobber went up and down 20 times, okay, in the 10 seconds. All right. Now, every time the bobber goes up and down once, that represents one wave coming through. One wave, one crest to push it up, one trough to pull it down. So one up and down is one wave passing through the location of the bobber. So if it goes up and down 20 times in 10 seconds, that means that there's 20 waves that pass through that spot in 10 seconds. Okay. Well, if 20 waves go through that spot in 10 seconds, how many go through in 1 second? I'll repeat. If 20 waves go through that location in 10 seconds, how many waves go through in 1 second? Yes, 2. 2 waves per second. Yeah, 2 waves per second past that spot where the bobber is. That's how often the waves go through that spot, or that's how frequent the waves go. That's how frequently the waves go through that spot. Okay, and that is the wave frequency. Frequency is the number of waves that pass a certain point in 1 second. That's wave frequency. That's how many waves pass a certain location in space in 1 second. All right, and we're going to denote that by F. Okay, lowercase f, not capital F. Capital F is force. Lowercase f is frequency. All right. Okay. So in my example, 20 waves pass a certain point in 10 seconds. And if 20 waves pass a certain point in 10 seconds, the number of waves per second is 20 waves over 10 seconds, which is 2 waves per second. Okay. All right. Sometimes in physics, we take units and we name them after somebody. Okay. And that's what they did with this. They took this unit and they named it after somebody. All right. And this person lived in the 1800s. He was German. And he was interested in finding a way to have communication transmission without wires. This is in the late 1800s. They had the telegraph, so they could send, information through wires, but he was interested in wireless communication. All right, and his work was instrumental in what later became known as radio. All right, his work made radio possible, the wireless transmission of information. Okay. Now he does not get credit for the first time doing this. That credit goes to an Italian guy named Marconi, who's credited with making the first radio transmission from one location to another. But this guy was instrumental in development of it, and also the development of radar, which is the detection over distance of objects. And of course, radar, one of the first applications of radar was in World War I, and everything else of radar. So without him, he made radar possible, one of the guys. Okay, and his name was Heinrich Hertz. Okay, so the unit of frequency is the hertz, named after Heinrich Hertz. Okay, and I should have a picture of the guy. And it's abbreviated HZ. Sometimes the H is capitalized, sometimes it isn't. I always capitalize it. So Hertz is the unit of frequency. All right, and I'm gonna actually get out of my PowerPoint for a minute. I wanna show you a picture. So I'm gonna need a let's see, get a Google image of this guy. Heinrich Hertz. What's his name? And this guy. Okay, and he lived in the latter part of the 1800s. All right, and he's German. Let's see, the man who discovered. Let's see. I didn't vet this, so I hope. Well, never mind. Anyway, if you, he made radio possible. Okay, let's get back into my presentation. Yeah. Okay. Now, if the frequency is 2 waves per second, how long does it take 1 wave to pass that point? If it takes 2 waves per second, how long for 1 wave? And when I say long, I mean what time? How many seconds does it take 1 wave to pass the spot? Anybody want to guess? Yeah, half a second. So 2 waves per second. I'm writing this down on my sheet here. 2 waves per second corresponds to 1/2 second per wave. All right. What if the wind comes up and the waves are more frequent. Okay, let's say instead that I have 10 waves per second as my frequency. Okay, if it takes 10 waves per second, actually, I'm getting ahead of myself. Excuse me. I'm going to come back to that, but hold on. I'm getting a little bit ahead of myself. If it takes, so it takes 1/2 second to pass. Yeah, if the frequency is 2 waves per second, it takes 1/2 second to pass. Okay, and then the time that it takes one wave to pass the spot is called the period. Okay, period is the time it takes for one wave to pass. And this is represented by capital T, not lowercase t, that's a general time. Cap T is the period. Okay, and anything that repeats itself, okay, anything in nature that's periodic, that is repeats itself, has a period, and the period is the time that it takes for one of those cycles. Okay, in this case, the period is 1/2 second. The Earth spins on its axis repeatedly. Okay, and the time it takes to happen once is 24 hours. All right, that's the period. The Earth also travels around the sun over and over and over and over again. And the time that it takes for one cycle to occur is 365 days. Okay, so that's the period for that. So the period is the time that it takes for something to repeat itself. All right, and in this case, it's 1/2 second. All right, now let's make the frequency 10 hertz or 10 waves per second. Okay, so that's the frequency, and this is the period. All right. If it's 2 waves per second, it's 1/2 second per wave. What if it's 10 waves per second? If the frequency is 10 waves per second, if 10 waves per second pass a certain location, what's the period? How long does it take for one of the waves to pass? You ready to tell me? Yeah, if 10 waves per second pass a spot, it's 1/10 of a second per wave. Okay, 10 waves for, so the first one takes 1/10 of a second, second one takes 1/10 of a second, third one takes 1/10 of a second. Okay, and on and on and on. And so each wave takes 1/10 of a second to pass your spot. All right. So can you see the relationship between frequency and period? Okay, if the frequency is 2, the period is 1/2. If the frequency is 10, the period is 1/10. All right. If the frequency was 100, the period would be 1/100th. Okay. So the relationship between frequency and period is a reciprocal relationship. Okay. And so we get this. Okay. The period is the reciprocal of the frequency. And oh, by the way, if you trade places, you can get the frequency is the reciprocal of the period. Okay. This should be the first entry into your equation bank for the second semester. Okay. First entry into your equation bank for the second semester. All right. Now, this is true of all waves, whether I'm talking about waves in water, whether I'm talking about waves in sound waves, light waves, any kind of waves. These relationships hold. Okay. All right. Next, let's say we had this. This is a snapshot in time of a bobber as a wave passes through the location. So this wave is traveling to the right. All right. Here's the bobber at this instant of time. At the next instant of time, this wave will have moved to the right a little bit. Okay. Question for you: which way does the bobber move? From this instant of time from this moment in time to the next moment in time when the wave is a little bit to the right? Does this bobber move up or does it move down? What do you think? Picture the wave traveling through to the right. Okay. Which way does the bobber move? Up or down? Let's find out. So I'm going to click here, and then down here, the wave is going to move. We'll see it. We'll kind of see go there and there. Notice that the bobber does move up. Those of you who said up were correct. Okay. Common misconception. Sometimes, see, they say the bobber just falls down the hill. No, that's not true. You have to picture it as the wave travels to the right. The crest of the wave is traveling to the right. So as the wave travels to the right, it pushes the bobber up to a crest. Okay. Later, as the wave travels through, the wave will pull the bobber down and the particles of water as well. Okay. All right. So we have to picture these moving through. All right. Okay. Next, I want to talk about phase. Now, phase, if I had to give it a definition, I would talk about it like this. It's a comparative description between 2 points on a wavefront. But I'll never ask you to give me the definition of phase. Okay. But we do want to apply it. All right. So I want you to picture something. You are actually, I also want you to get another picture, sketch yourself a transverse wave. And hold on just a minute. And have at least 3 crests in the shot. So draw one like this. Okay. Now, and this wave is going to be passing to the right. All right. Now, let's say that you are out with a friend in a boat, and the bobbers are you have a bobber in the water, your friend has a bobber in the water, and the fish aren't biting, so the surface is glass-like. Okay. And the speedboat goes by, and you're bored, so you watch the waves pass through first the location of your bobber and then the location of your friend's bobber. Okay. And your bobber, and at this snapshot, at this instant of time, your bobber is right here. Okay. And you see your friend's bobber as well. And you notice something a little bit unusual. Okay. You notice that the wave is causing both of your bobbers to move up and down completely in sync. That is, when your bobber gets to a crest, your friend's bobber gets to a crest. When your bobber gets to a trough, your friend's bobber gets to a trough. They're moving completely in sync or in phase. They're moving completely in phase with each other. Okay. Question for you. Question for you. Question for you. Where your friend's bobber is somewhere to the right of your bobber. Where? So I want you to draw this is bobber A. I want you to draw bobber B. Where is bobber B along this wavefront? So that they're completely moving up and down together in sync. Okay? Draw bobber B on your paper. And then hold it up to the screen. I want to see it. Turn your cameras on. Hold your notebooks up to the screen. Where is, nice and close so I can see. Okay, where is bobber B? All right, I'm seeing a couple of correct responses. Okay, not enough cameras are on. Maybe somebody's out there. Am I talking to empty space? I know I'm talking to some of you. All right, so yeah, lots of correct responses. Yes, bobber B is here. Okay. All right. Bobber B is there. Yeah. Okay, now, question for you. How far apart are bobbers A and B in terms of wavelength? How far apart are bobbers A and B? Bobbers A and B are completely in phase with each other. Okay. How far apart are they on the wavefront? What's the distance from here to here? How many wavelengths apart? And And the answer, I'm saying yes, one wavelength apart. Okay, now you don't have to write all this stuff down. Okay, you don't have to write down word for word, because all I'm doing is, kind of just writing down what I talked about. Okay, A and B are in phase if they move completely together. Okay, and they are exactly one wavelength apart. Okay. All right. Now, let's say you have another friend in the boat. Well, okay, and your friend, let's say, and that friend has a third bobber in the water, bobber C, and all three bobbers are in phase. All three bobbers are in phase. Where is bobber C on the wavefront? Draw. Where is bobber C on the wavefront? Okay. Where should I put bobber C on my diagram? All right. Where do you think? Hold it up to the screen. I want to see. Where is bobber C? Where is bobber C? Yep. 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 Bobber C is right there. Yeah. Bobber C is there. Bobber C is here. Notice B and C are, again, one wavelength apart. How far apart are A and C? How far apart are bobbers A and C? Well, A and C are exactly 2 wavelengths apart. Yeah, exactly 2. All right, general statement now. 2 points on a wavefront are in phase when when they differ, okay, by 1 wavelength or 2 wavelengths or any integer wavelength apart. 6 wavelengths, 18 wavelengths. If they're exactly that many wavelengths apart, then they are in phase and they will move exactly together. Okay. All right. All right. Now, as it happens, you have a fourth friend in the boat. So there's a fourth bobber in the water, bobber D. But what's weird about this is that the bobber D is not in phase with bobbers A, B, and C. It's not doing the same thing as A and B. As a matter of fact, just talking about bobber A in relation to bobber A, it is doing exactly the opposite. That is, when bobber A is moving up, bobber D is moving down. When bobber A reaches a crest, bobber D reaches a trough. When bobber A reaches a trough, bobber D reaches a crest. They are not only out of phase, they are perfectly out of phase, or 180 degrees out of phase. Okay? Now, excuse me, I didn't want to do that. Where, and I'm going to say bobber D is between bobbers A and B. So somewhere in here is bobber D. Where? Where on the wavefront is bobber D, so that bobbers A and D are 180 degrees out of phase. They're doing exactly the opposite of each other. Where is it? Okay. Put in bobber D and show me on the screen. Where is bobber D? Where should I draw bobber D? Anybody wanna? Okay, good. I'm seeing. Good. Bobber D. Yes, very nicely done. Bobber D is there. Right. Bobber D is there. Okay. All right. Let's see. Bobber D is there. Okay. Now, how far apart in terms of wavelength are bobbers A and D? A and B are one wavelength apart, exactly one wavelength. How far apart are bobbers A and D? Yes. Yes. Thank you, Juliana. That is correct. Okay. They're exactly 1/2 wavelength apart. Okay. All right. How far apart are bobbers D and C? Well, bobbers D and B are also 180 degrees out of phase, and are exactly 1/2 a wavelength apart also. D and C are also 180 degrees out of phase. Okay. How far apart are bobbers D and C? How far apart are bobbers D and C? Yeah. Yes. Yes. Nicely done. It's a wavelength and then another half. 1.5 wavelengths. Okay. And that's going to be true of all the rest. If it's 1.5 or 2.5 or 15.5, they will be 180 degrees out of phase. Okay. Another way to say that is a 1.5 is to say 3/2. Okay. So in general, 2 points on a wavefront are 180 degrees out of phase when they differ by 1/2 a wavelength, or 3/2, or 5/2, or 7/2, or any odd half integer wavelength. They will be 180 degrees out of phase. Okay, so with phase, we don't really give a definition for it. Instead, we take 2 points on a wavefront and we compare them. We compare their phase, okay, whether they're in phase or out of phase, and if they are, whether they're in phase or 180 degrees out of phase, and that tells us the distance between them on the wavefront. Okay, so phase is really a comparison thing. Okay, and we're going to bring that up in certain cases. All right, now the next thing to talk about is speed of a wave, but I don't want to go there because, for one thing, I want to have equipment in my room I want to have equipment in my room. Let me turn my camera, change the camera. I want to show you this with stuff in my room. So I'm going to stop here. Okay. Yeah. Now, tomorrow, I'm going to have you guys watch a video that I made of waves in my wave tank. Okay. And I don't have a wave tank here. It's in my previous school. But I want to. I filmed some phenomena about wave propagation and how waves reflect from boundaries. And I made a quick little video of that. It's like 12 minutes long or something like that. And I'm going to have you guys watch that and work on Waves Worksheet 2. Shortly, I'm going to send you to breakout rooms to start working on Waves Worksheet 1. All right, now. So tomorrow you're just going to be viewing something and making sketches primarily. All right, it's not difficult, but so don't freak out. But I wanted to show you some stuff in the wave tank. Okay, and that'll be tomorrow. I don't think it will take all of the 30 minutes, but if you want to view it a couple times, then you can. All right, the video is like between 11 and 12 minutes long, so that'll be tomorrow. We're staying very general with this wave vocabulary. There's a couple more things I need to talk about that are particular to all types of waves, and then we'll focus in on particular types of waves. Okay, namely sound, which we'll spend a good deal of time on, and light, which we'll spend a lot of time on actually. And actually, like electricity also involves waves in a sense, and so does magnetism. Okay, so I'll bring that into it as well. All right. Okay, any questions for me? I know it's a lot of vocab heavy. I tried to spice it up a little bit, but it's pretty much vocab heavy, at least to begin. All right, well then I'm going to ask you to get into, let's see, do I have this? I want to share a screen one more time, and I'm not sure. Okay, I'm going to get out of here. Got to get into there and then get out of there. All right. Talk about that later. And I want to get into Schoology. I got to remove that toolbar. Do I have that? Is this? Oh, yeah. Wow. Okay. So yeah. So in this week's Schoology folder, I want you to access this thing that says "Don't Make Waves 2021." Okay. And when you open that, it's going to PDF. Okay. It's going to look like. It's going to look like. It's going to look like this once it pops up. And you can download this and print it if you want, or just write this stuff on your own sheet of paper. Makes no difference to me. But we can do numbers 1. We can do number 2. We can do number 3. You can't do number 4. Can't do number 5. Talking about phase for number 6, you could do. All right. So for the rest of the time, and it's going on 20 minutes, the definitions are going to take a while. But please complete numbers 1, 2, 3, and 6. Okay. All right. And I'm going to give you the rest of the time to work on this. Tomorrow, from the wave tank, you can do Waves Worksheet 2. All right. That's where you'll access it for tomorrow. Okay.
Where do we find the Wave Worksheet 1?
When is the Waves? Did you ask when is it due? I didn't hear you.
No, just where do we find it? I'm not seeing. I see Wave Worksheet 2.
Could you repeat your question?
Where are we supposed to find Wave Worksheet 1?
The Waves Worksheet 1 is the Don't Make Waves one.
Oh, okay.
Should I rename that?
No,
let me edit this. Okay. I try to be a little bit more imaginative with my names, but I'll call it Waves Worksheet 1. If it's easier for you guys, then that's what I'll do. So there, is that better? So yeah, so I'll send you to breakout rooms, and you should have goodly amount of time to work on that. Okay, and then we'll reconvene at the end of the period. All right.